So I wanted to start by saying a little bit about the construction of the R-squared statistic. So just in words, the R-squared statistic is the proportion of the variability in the data that the model describes, and ideally the higher the R-squared, the better. So in terms of these equations then, so R-squared is the variation explained by the model divided by the total variation in the data. So you can write this as SSR over SST, where SSR is the sum of squares for regression, SST is the total sum of squares. You can then write the top line as the difference between the total sum of squares and the sum of squared errors from the regression model, and then you can write this in the bottom row as this fraction SSE ST. Now we'll go through some R-squared calculations in the next lecture, which is probably more useful for you. Okay, I don't want to overdo it with this slide. The reason it's want to sort of show you these derivations in the notes demonstrates that the highest R-squared value that is possible is 1, S is equal to 0, and the regression explains absolutely everything in the data, and the lowest value of R-squared could be 0 if the sum of squares error is exactly the same as the total sum of squares. Then you would get 1 minus 1 equals 0, so the minimum value of R-squared is 0. So I wanted now to talk about how you run the regression in R. Now, when you do this, you've got to think a little bit about how the program works and think R for robot. Okay, so the thing will do exactly what you tell it to do, nothing more, nothing less. Now, the basic command used is LM for linear model. So this is a maths thing, and there's a deliberate reason why it's called LM. You then specify the Y variable, then the X variables with a tilde sign in between. And this is a sort of mathematical motivation, and this tilde means sign between the different x variables. So I'll show you this. So again, think R is robot. It's sort of very clever, but also very stupid at the same time. It will do exactly what you tell it to do, nothing more, nothing less. And the best way to do this is to run the regression analysis and store the results. R to summarize results for you in a second step. Summary command in R summary, so you can sort of see this sort of two-step process repeated at the bottom in terms of the actual R code. We'll run the regression, model, price related to the real stock price, run the computation, and then summary.lm. This will then the results. So there's this sort of two-step process: run the regression, the analysis, and then summarize results step. So in previews, it's perhaps a little bit more intuitive. So what you would do from the module page on Canvas, so open this file, and what you need to do is quick equation, and then you want real gold price, C for constant, real stock price, and the order of this is almost musical. Y is C for constant, and the X variables listed one by one. If you've got more than one X variable, you have a space between each of the X variables, and then click OK. So what you should sort of see here then is that there is a sort of set rhyme and reason as to how these things are set out, both in R and E views, and it's nice and easy to sort of fit a simple linear regression model as we've got here, which describes the relationship between the real gold price and the real stock price. It's essentially the same set of commands to fit a more complex multiple linear regression model, and this reflects that, in contrast to some of the sort of slightly trite jargon used by some of these textbooks, actually these are all versions of the multiple linear regression model, and the maths and the coding used is the same in each case. So any statistical software package will produce a wealth of redundant information. Really, the skill is picking out the bits of the information that are produced that you can really use. It is probable that for this course you're probably only going to be using a small fraction of the total functionality that these software packages have. Okay, and the value added isn't just producing loads and loads of results. The value added is actually picking out precisely the bits of information that you need. So then is just out precisely the useful and informative bits of information. Things to sort of look for as part of this course would be the statistic. What you will see is that there are some slight differences between whether you've got a simple linear regression model as here, and or if you've got instead a more general multiple linear regression model that will go through towards the end of the lecture. Okay, and we've talked about the R-squared statistics. The rest of the lecture try and discuss what these TNF statistics are really doing. So I think the T statistic is for individual significance, is testing for collective or joint significance of a set of variables. So recall then, so if we're looking at regression, although it's a multifaceted subject and really where finance research methods and the subject of statistics really begins, the basic question is always exactly the same. What happens to y as x increases? Does y increase, does y decrease, or does nothing at all happen? Okay, and then as I said before, these are all very simple concepts and easy to visualize pictorially. Okay, so there are some equations coming up towards the end of this lecture and in the next lecture. Okay, but I think this is sort of easier, at least in spirit, if you can sort of recognize that all these things are a different way of drawing these same pictures that we've seen time and time again. Okay, and these pictures, as I keep repeating, are themselves just a repetition of things you will have seen before at high school maths. Okay, and so what you're doing with the T statistic is just giving you a rigorous way of answering this question. What happens to y as x increases? Does y also increase? Does y decrease? Or does nothing at all happen? And the idea would be that if the variable is significant measured by the t-test, then this would indicate that as x increases, nothing happens to y. So just to re-emphasize then, so if you've got a positive gradient, this just means that as x increases, y increases. Equivalently, that as x decreases, y decreases. And this is something that you can now test for rigorously using a t-test. Okay, lots and lots of possible applications in economics and finance, and again, just a repetition of the sorts of things you'll have seen before in high school maths. So the classic example I've kept banging on about in the last couple of lectures. So if you imagine x being the fuel costs and y being the price of goods in the supermarket, so as fuel costs increase, you might reasonably imagine that the goods in the supermarkets also increase in price. Also, if x decreases, then you might reasonably imagine there's a cost saving that could be passed on to consumers, and that the price of goods in the supermarket could also decrease in price. So, as I said before, this is a repetition of really quite simple concepts. Now, the idea is that if you have this sort of picture happening, what would happen is that the t statistic would be significant and the estimated coefficient would be positive. So the maths involved just gives you a different way of drawing the same graph. So so a negative gradient, so very simply, as x increases, y decreases. Equivalently, as x decreases, y increases. And the basic idea is that if you were running these t-tests, if the t-test was significant and the estimated coefficient was negative, then although you've got some maths and statistical notation kicking around the place, this is just an equivalent way of drawing the same graph. Okay, and this is sort of repeating the same concepts we had in the early lectures, and is itself a repetition of some of the things you've seen before at high school maths, even if you're now using some slightly more complex terminology. And so This idea of negative gradient obviously got broad application in economics and finance. So the examples I was mentioning before, if you've got X being the fuel price and Y being the profits of a haulage company, you might reasonably expect to find that as the fuel price increases, the profit for the haulage company decreases. Equivalently, as the fuel price decreases, then you might expect to find that the profit of the haulage company increases. Okay, so repetition of this idea, it's just these t statistics give you an equivalent way of visualizing and systematically testing for which of these classical graphical patterns apply. Zero gradient, so the idea here is that changes in x do not affect y, so if you have high values of x, nothing happens to y. If you have low values of x, again, nothing happens to y. Now, how this would work is that if you start with a null hypothesis that the regression coefficient is equal to 0, you start off with this sort of baseline case here where the effect of x upon y is just purely flat, and then you look for evidence against that to see which of the previous two graphs apply. So if this zero gradient doesn't occur and the regression coefficient is indeed statistically significant, it's then natural to look, is the thing positive indicating a positive correlation, or is the thing negative indicating a negative correlation? And again, all these t-statistics will do is give you a different way of visualizing these same graphs. Now there's a lot of repetition here, both from the early lecture material and from material you'll have seen before at high school maths. Okay, but I think it's important to draw this parallel because although parts of regression might look difficult, in essence it's just a alternative way of rigorously same analysis which of these classical graphical patterns apply. This is zero gradient, positive gradient, or a negative gradient. So I'm afraid I've run out of graphs for the time being, and some mathematics and some equations are unavoidable. So if you start with this two-variable linear regression model, also called the simple regression model, so you've got one variable, one x variable. See then what this is doing. If you think back to these past three graphs, we want to see which of these graphs best fits our data. The graph where there's no gradient, is there instead a positive gradient or a negative gradient? Now it's a slightly strange way of thinking, but it turns out the easiest way to do this is to test this hypothesis here, that the value of beta 2 equals 0, and then look for evidence against that. So if you look back to these last three graphs, the best way to sort of visualize this is you start off by assuming you've got this flat line where there's a zero gradient, and then if you find evidence against that, is the gradient either positive or negative? So equivalently, if you do find that beta 2 is not equal to 0 and there is a relationship between x and y, as x increases, what happens to y? Does it increase or does it decrease? Okay, so what you can hopefully sort of see here, it's grounded in a graphical and in essence very simple way of seeing the world. So if you run a regression analysis in R or E views, you get something that looks a little bit like this. And the key thing to sort of remember here is that R or E views or any other software package you choose to mention will inevitably produce some irrelevant information, and your job as a Yale analyst is to provide the value added by picking out the useful bits of the information. So what you've got is this table here. The first row of the table refers to the intercept or constant term. Informative because usually you would fit an intercept or constant term. It turns out it's the second row of this table downwards that is important. And see a multiple example later in the lecture where again it's the second row downwards of this table which is the important bit where the action is. And what you have here, if you look at the p-values, so this real stock price is significant precisely because this p-value here is 0.85. and then the coefficient is negative. So this indicates that in this example, indeed, we do have a relationship between precise because the p-value is less than 0.05, the coefficient is negative and statistically significant.